So we're still having more people come in, and I think it'll be pretty full by the end. Today we are very excited to give a tutorial on LLMs and inference algorithms, and specifically meta-generation algorithms for large language models. So at its core, today's tutorial is about algorithms for generating outputs with a language model. And so why should you be as excited and as interested in this topic as we all are? Well, a lot of people in the field right now are thinking very hard about how we can use compute at test time after a language model has been trained in order to improve the performance of the generation system. And it's actually exactly this will be the topic of today's tutorial. And also, language models themselves are just incredibly exciting. It seems like every day they have some new capability, ranging from solving Olympiad problems to writing really complex code in your code base. And essentially anything that you could frame as, any task that you could frame as generating a sequence, language models might be able to help you with. And when we think about the progress in language models, we can think about it from the perspective of scale. So the first wave of scale was centered around scaling the amount of computation that is used to pre-train a model. So here's a really famous result from OpenAI. And what they show is that as you increase the amount of compute that's used to pre-train a language model, which is related to the size of the model as well as the number of tokens that the model is trained on, the performance of the model predictably improves in terms of test loss. And so this is really exciting. But since then, at least so far, this hasn't been sufficient to get these language models to perform all the tasks that we want them to. So there's been a second wave focused on what's called post-training. And here's an example where you, for instance, collect as many input-output pairs as you can, and then you fine-tune the language model on them, and it can do better at these tasks and even generalize to some new ones. And so this has led to these incredibly flexible, incredibly useful assistants that many of you may have used. But similarly, at least so far, this hasn't proven sufficient for all of the tasks that people want to use language models for. And so currently, the field is undergoing a kind of third shift, and it's focused on test time scaling. So here we take a model that's already trained, and we want to design methods that can improve its performance at test time or inference time or generation time. And so here's a really stunning result recently from OpenAI. And you can see that they've developed some method where here on the x-axis, they're increasing the amount of test time compute. And on the y-axis, they're seeing these improvements in this pretty difficult mathematical reasoning benchmark. And so how might this be possible? Well, when you think about it, these language models are kind of token generators, and you can increase the amount of computation that you're using by just generating more with them. I mean, after all, when you generate one token, you're doing a feed-forward pass through a neural network, and that is in some sense spending computation. And so here's a really influential method called chain of thought, and they simply ask the model to generate these intermediate thought tokens, which are shown in green. And it turns out that although this might sound simple, it can have a kind of profound effect on how these models scale on different tasks. So for example, on the right-hand side, you can see that if you just used standard prompting, which is asking the model to answer directly, the models didn't seem to do too well on these kind of reasoning style tasks. However, if you use this intermediate thought, now the scaling behavior completely changes. Second, you can just call these generators multiple times. So here's a famous example called AlphaCode. And here they were trying to generate programs. And you can see on the right-hand side that at test time, they don't just have the model generate one output program. Instead, they have it generate thousands or even millions of output programs. And then they filter them and cluster them and eventually just consider a small set to be the output of the system. And this as well can have a huge impact on the success rate. So you can see here on the x-axis, as the number of samples is scaled up, the pass rate is increasing a lot for a wide range of model sizes. And we've seen these types of curves appearing in more and more domains recently, ranging from mathematical reasoning to digital agents, and even in these very flexible general purpose instruction following models. And then third, another shift that's occurring in the field is moving from just a language model operating on its own to a more compound AI system, where you have the language model, but now also things like a learned evaluation model. You might have the model calling out the tools, like a calculator or a code interpreter. And so all of these things give you ways of potentially offloading some of the computation to these more reliable tools. And so today's tutorial will give you a conceptual framework for thinking about how to bring these three things together into a generation system. And we'll look at some of the common patterns and techniques that have been designed for creating these generation algorithms and scaling them up. So what is a meta-generator? Well, first, a generator just refers to any algorithm that takes in an input sequence in a language model and gives you an output sequence. If you've ever used one of these LLM APIs, you can think of this as being a generator. And so in the first part of the talk, we'll go over what are the kind of traditional algorithms for just generating one sequence with a language model. Then we can use those algorithms and treat them as a black box. And we could design these higher level strategies for calling generators and incorporating external information like other models or tools. And so a really simple example is you could instead call your API multiple times and then select the best output with some other model that you have. And again, why would you want to do this? Well, if you design your meta-generator correctly, we'll see that you can use it to improve task performance by just generating more and more. It gives you some way of describing these systems that have multiple models and that incorporate information that's outside of the language model. So the tutorial is structured into three different parts. In the first part, we'll go over primitive generators, so how you just generate one sequence from a language model. Then we'll talk about these higher level meta-generation strategies for calling generators multiple times and incorporating external information. And then finally, we'll talk about an extremely important aspect for scaling these up, which is efficiency. How do you generate quickly and efficiently, and even take advantage of the particular form of some meta-generators? Then we'll have a panel session at the end, so please be sure to stick around for the whole time. In terms of the presenters, Matt, who's a PhD student at USC, will present the first part. Then I'll come back and present the second part on meta-generation. And Haley, who did this work while at Eleuther AI and is now at Anthropic, will present the third part on efficiency. We're also incredibly honored to have this amazing panel. We'll hear from Beatty Chen from CMU, Nuha Ziri from AI2, Rishab Agarwal from DeepMind and McGill, Jacob Forrester from Oxford and Meta AI, Noam Brown from OpenAI, and Ilya Kulikov from Meta AI, who's also part of the tutorial team, will be the moderator. So this tutorial is ultimately based on a survey paper that was just published at TMLR. You can see it at the bottom here. And all of the authors shown here really contributed to everything in this tutorial. So all of the thanks goes to all the people shown here. We also have a website with all of the resources. You can see the slides. If you're sitting in the back of the room and the font's too small, you could open it up on your laptop. We also have code examples that we won't even have time to go into today, as well as a pretty long reading list. So we really want it to be someplace that you go not only during the tutorial, but even after for further study. So with that, I'll hand it off to Matt to talk about primitive generators.
All right. Hello, everyone. I'm Matthew Finlayson. I'm a PhD student at USC. And today I'll be talking to you about primitive generators. And when I say primitive here, I don't mean like simple. I guess these are simple methods. But what this primitive means is these are the primitives with which we're going to build these meta generation algorithms. These are kind of like the building blocks of generation with language models. Great. So let's see. Somehow I've gone on to, there we go. Great. So primitive generators are the building blocks that we're going to use for these more complex, more sophisticated generation algorithms. So to start, let's talk a little bit about how token-level generation works with autoregressive language models. So if you go to your favorite language model API, almost all of these language models are causal language models, which means they take an input sequence and they produce a probability distribution over what the vocabulary of the model, the vocabulary being all the tokens that could come next in the sequence. And so based on this score that's assigned to each token by the language model, you have to choose one of these tokens and append it to the sequence, and then autoregressively feed this sequence back into the language model, which will give you, again, a probability distribution over next tokens. Let's see. So all of the generation algorithms I'll be talking about today are concerned with how do you choose the next token. Basically, at each point in this decoding algorithm, you're given a huge set of choices and some guidance from the language model in the form of scores for which path you're going to take. And so this becomes basically a massive search problem, one that's so huge that you can't exhaustively check every sequence. And so we have to basically come up with some kind of objective. Like, what are we trying to do here? How do we make these choices to get a good generation out of our language model? So there's a few different ways of conceptualizing generation from language models. One of the earliest and historically very popular ways of thinking about decoding is as an optimization problem, where you want to maximize some score. Maybe it's the probability of the sequence. Then we're going to talk a little bit about sampling, which is basically the dominant method for primitive generators today. And then lastly, we'll talk a little bit about constrained generations. So what happens when you want to generate according to some kind of structural constraint in the outputs. All right, so let's get started with decoding as optimization. So kind of one of the earliest and for a long time very popular way of decoding from language models was to try to maximize the probability of the output sequence from the language model. This is kind of maybe a naive, but it's a very straightforward objective. You want to find the most likely continuation given the prefix. So kind of like the first most obvious way of doing this is greedy decoding, where at each step during generation you just take the highest scoring token, the most likely token. This is for a long time. I guess this is still a very popular way of generating from your language model. It's very straightforward. It doesn't guarantee you the most likely sequence. So here we have our prefix Taylor Swift is A, and the continuation, the most likely continuation at each step is former followed by contestant, and then followed by on. And it gives you this, you can basically score the probability of this continuation by multiplying the probabilities together. Unfortunately, this does not give you necessarily the most probable sequence, because, for instance, if you took singer, which is less probable at that first generation step, and then you decode greedily after that, you actually end up with a probability which is higher. So basically the locally most likely token might not give you the globally most likely sequence. So for computer scientists here, you might recognize this as kind of like, oh, that's just the greedy algorithm for, and the more exact algorithm would be like some kind of breadth first search or exhaustive search. Because we can't feasibly do that for a language model with tens or hundreds of thousands of tokens in its vocabulary, kind of a middle ground here is to use beam search. So beam search is historically very popular. What you do is basically at every generation step, you choose the top k most likely tokens, and then you expand on these tokens, basically pruning your search tree. So here we have A and the as the most likely next tokens. You expand both of them and then take the two most likely continuations, which actually both come from the branch, and you continue on until you have generated a sequence, and basically the bigger your beam size, the more likely you are to get the most likely sequence out of this. Cool. And this kind of probability maximization objective can be very effective, especially for closed-ended tasks. You can see here that beam search outperforms greedy for all of these translation and question answering tasks. And for other tasks, like basically blue score can increase with your beam size. So it seems like this is a pretty good way of generating from language models. Unfortunately, MAP has a few drawbacks, and for that reason, it's not actually that popular today. And so some of these kind of drawbacks from probability maximization are as follows. So the first of these is repetition traps. So the model, especially for older models, will kind of fall into this pattern where they generate very repetitive sequences. Here GPT-2 finds the phrase singer-songwriter, and it just loves this phrase and will keep repeating it ad nauseum. So people deal with these types of repetition traps in various ways. One is repetition penalty, so basically penalizing words. You can see this in like OpenAI's API. You can also account for this during training. So Sean's work actually tried out actually during training time, discouraging the model from repeating tokens. The second pitfall we're going to talk about is short sequences. So because as the sequence grows, it monotonically decreases probability, you can end up with the most likely sequence at the end of the day being the empty sequence. People have dealt with this by basically normalizing the probability of sequences by their length. This is not very well theoretically motivated, but it's kind of a stopgap in practice. And then the third pitfall of probability maximization is actually information theoretic argument about the most likely sequence. And I think this is actually one of the most interesting reasons why you should beware when you're using probability maximization. And to do this, let's think about like kind of a thought experiment. Let's say you had a coin that was just slightly biased towards head, and you flipped this coin 100 times. The most likely outcome from this sequence is actually 100 flips with heads. That's the most likely outcome. But if you actually saw that in practice, you might be a little bit surprised, because the probability of heads is only slightly greater than the probability of tails. So this is an example of an outcome that's atypical, and there's actually like an information theoretic concept of atypicality, where like the most likely is not necessarily something that you would expect. And in terms of linguistics, you can also think about when you speak, you're trying to convey information. And the most likely sequence is actually going to contain the least amount of information. So at the end of the day, there have been numerous studies that have found that actually probability maximization isn't good unto itself, but in practice, approximate map, so greedy decoding and like narrow beam size, usually works pretty well for language models. So it's kind of this probability maximization may have looked like a good choice, but maybe it did well for other reasons. So let's talk about some of those other reasons. So we're going to get into sampling now. So sampling is kind of the dominant way of generating from language models these days. Here's an example from the Together AI playground where you can see these parameters that you can play with. So immediately you see temperature, top P, and top K. These are all sampling methods for language models. So the basic, the most simple sampling algorithm that you can use for a language model is called ancestral sampling, which is where you just trust the language model's probability distribution, and you sample the next token according to that distribution. And this is actually equivalent to sampling sequences directly from the language model. So the language model defines an implicit probability distribution over sequences. This is equivalent to sampling directly from that probability distribution. So ancestral sampling is not without its own drawbacks. So we saw with greedy decoding or other map methods, you get a lot of repetition. Ancestral kind of has this opposite problem where you get very diverse outputs, but they tend to be incoherent. They can kind of take random paths and end up not reading very well. And the reason for this is that it's the language model probability distribution tends to assign too much probability to the tail of the distribution. So these low probability tokens, somehow the model is assigning too much probability to them. So even though each individual token doesn't have that much probability on it, in aggregate, you end up being very likely to sample a low probability token. This is known as like a heavy tail on the distribution. So the sampling parameters that you saw on that API example, one of them was top K. And the other ones are kind of similar to top K in that what they do is they chop off the tail of the distribution and make it so that you can only sample from the most likely tokens. So this kind of chopping off the tail is known as truncation sampling, and there are a plethora of truncation sampling methods. I have a few listed here. They all have kind of a different heuristic for how to choose that threshold below which you will truncate all the tokens. And to kind of get an idea of why you might need all these different heuristics, let's look at these two probability distributions. So one of the earliest truncation sampling methods, top K sampling, is you just choose an integer and you only consider the top K tokens in the distribution. And no matter what the distribution looks like, you always use this heuristic. With top P, on the other hand, you use the cumulative distribution, and you basically mandate that the cumulative distribution of the ordered tokens doesn't add up more than P. So for instance, here's top P is 0.9. The sum of these top tokens is 0.9, whereas with this distribution, the sum of the probabilities of all of these tokens is 0.9. And so you kind of get this dynamic choice of your threshold for truncation. And this has been shown to outperform simpler methods like top K. And all of the other sampling methods that I've shown are basically variants of this. Okay, so an alternative to truncation sampling, which is also very popular, is called temperature sampling. So what temperature does is instead of truncating the distribution, it just adjusts how peaky the distribution is. So you do this by basically adding a coefficient to the logits, and after you take the softmax, that results, if you have a high temperature, it makes the distribution more uniform. If you have a low temperature, then you get more peaky distribution. And if you set the temperature to be 0, what you end up with is greedy decoding. Only the most likely token will have probability on it. And you can see this in this example. You've probably heard enough of Taylor Swift recently, but all our examples are Taylor Swift. So with temperature at 0.5, you see this very peaky distribution. With higher temperatures, you see this very uniform distribution. And all of these sampling algorithms are very simple. You just require maybe like one line of code to implement them. I have several of them implemented here. You can check out our code for reference in implementations later. And you probably don't even need to write that one line of code because most modern generation frameworks, such as VLLM or Hugging Face, you can basically just pass the sampling parameters directly to the generation function. Okay, so kind of one of the big mysteries here in decoding research is why the model puts too much probability on the tail of a distribution. There's a few different theories, a few different explanations. One is undertraining, so the model just doesn't know what the true next token distribution should be, so if you trained it for longer, maybe this problem would go away. Another explanation is this behavior of the cross-entropy loss function. So during training, if you underestimate the probability of a token, then you get a much larger penalty than if you overestimate it. So the model does better during training if it basically covers all the tokens that might come next, even if they won't actually. Another kind of explanation, this comes from my own research, is that the model architecture itself puts constraints on what the model can output. And these constraints can also cause basically misalignment between the model's output distribution just because it can't express the correct distribution. All right, so we've seen a few different kind of ways of adjusting the output distribution of the model. These all kind of fall under this framework of sampling adapters. So a sampling adapter is when you take the model distribution and you make some adjustment to the probabilities. And you can also incorporate knowledge from outside of the model's distribution. So for instance, in contrastive decoding, you adjust the next token probability distribution by basically adjusting it by an anti-expert model. So you have a model that you want to emulate the behavior of, and you have a model that you don't want to emulate. And you combine those two distributions to move the distribution more towards the desirable model. In our survey paper, we cover a ton of different sampling adapters, and so I recommend you take a look there. Lots of them have different properties that are favorable for different types of tasks. All right, and now we're going to kind of go over the the third part of this section, which is constrained decoding. So when you're embedding a language model into a larger system, say into kind of a larger program, you want the language model to be able to communicate with other parts of the program. And by nature, language models are trained to output natural language, which doesn't always play well with your Python program. So one thing that you can do here is you can constrain the language model to output something that the rest of your program can understand. For instance, JSON. You see this in a lot of APIs where you have some type of JSON mode, where you can specify a JSON schema and the outputs of the model will have to adhere to that schema. And we're going to get a little bit into how that works. Okay, so here's our kind of example that we're going to work through. Let's say you want to extract the name and birth year of a celebrity from some natural language. So you give the language model this instruction to follow the schema and encode the information in the sentence, Taylor Swift was born December 13, 1989. So if you just feed this to a language model, you might get something like this, where the information is now in a JSON format, but it doesn't necessarily quite match the format that you wanted it to take. And for like a well-trained model, maybe you would get it most of the time, but there's just that small rate of error where you're going to get something that doesn't match the schema. So how do we force the model to follow the schema? Well, one approach, which is taken in a few different libraries, such as guidance, is to take the schema and compile it into some kind of parser. So in this case, we've taken the JSON schema and we've encoded it as a state machine. And the state machine can tell you what the list of like valid next generations are. So for instance, here, when you start, there's only one valid generation, which is the open brace. So the model generates the open brace, and then you get to the next state, and there's kind of a fork in the road here where it can either generate name or birth year. It chooses to generate name, and then it fills out what that name is, and then it chooses birth year. And here you can see that basically if there's the model wants to generate things, like the most likely tokens don't match the JSON schema. So for instance, it wants to open a parentheses, or sorry, open quote, but by constraining the model to only generate integers at this point, you can get it to generate the correct output. And eventually you get to the end and you have your valid JSON. Even though you might be using a weak model like GPT-2, suddenly it's able to follow this instruction to generate valid JSON. So this type of templated hybrid generation where you have a parser plus a language model can actually end up giving you speed-ups in performance. So if there's only one valid path, you can just automatically take that path. But it can also reduce the performance of your model, and we'll see why. So templated generation can force these types of unnatural token boundaries. So for instance, if your template gives it this input, you might see something like this, where the model generates like a space before the double forward slash. And that's because during training, the tokenizer has given the model examples of this kind of 2-token version, but it hasn't really seen this 3-token version during training. So some language model constrained generation libraries do this thing called token healing, where it rewinds the tokenizer and then enforces that the next token has to start with this, like the remaining text. So you hear it basically eliminates the HTTPS generation, but it selects the correct next token. Another way you could fix this in a language model is during training, you could apply tokenizer regularization, where you kind of randomize the way that the tokenizer tokenizes the sequence during training. And this can make it more robust to kind of gotchas like this. All right, so to kind of summarize what we've talked about here, we've looked at basically the building blocks for generation. These are kind of the low-level generation algorithms that you're going to use in your meta-generation algorithms. There's kind of two ways to look at generation. One is optimization, the other is sampling. Both have their uses. Most language models today that you see will use sampling. And basically there's this diversity coherence trade-off when you're sampling. You can either be more greedy or you can be more diverse, more uniform in your distributions. And then thirdly, you can use kind of parsers or state machines to constrain your outputs in order to conform to structural constraints. So yeah, these are our building blocks, and Sean will come back up here and talk a little bit more about meta generation. Thank you.
Okay, so yeah, as Matt mentioned, now we'll move to meta generators, which will kind of treat the algorithms that we just talked about as a black box. And these will be kind of higher level strategies for calling the generators as well as incorporating different types of external information. So let's think about like how we could formalize the goal that you might have when you're designing a generation system. You could say that your goal is to design a system that gives you acceptable sequences for some notion of acceptability. So let's say you're solving math problems, then you want your output to be correct. Or if you're deploying a chatbot, maybe you want the responses to be preferred by the humans that are reading it. And in some sense, we could think of the algorithms that we just saw as different ways of getting outputs that are probable according to a language model. But then there's this issue, which is like, what if there's a kind of misalignment? What if these outputs that we get are not actually acceptable for what we want the generator to be doing? So the techniques that I'll talk about in a bit try to get at this with kind of two different underlying ideas. So one is that we can somehow incorporate information that is outside of the language model into the generation procedure. So one example of this is, let's say you learn an evaluator model, and your evaluator model will take in an output, and it will actually approximate this notion of acceptability. Then, and so these evaluator models, if you read through the literature, can go by different names. So I'll try to use the term reward model throughout the talk, but if you read through papers, you'll see all of the different names listed here. And then second, you could think about like, we don't just have to call the generator once. We can actually keep calling it over and over, and in some sense try to search for a good sequence. And for example, if we combine that with our evaluation model, we might eventually generate an output that our evaluation model says is acceptable, and now we have a good output from our generation system. So let's look at a concrete example. So here we want to solve this math problem. You don't have to read through the whole problem or solution. But we have the input x, and we ask the model to generate the solution z, and then finally an answer y at the end. And let's look at what happens if we have an oracle verifier or evaluator model. So the oracle would tell us, definitively, is the answer to this question correct or not? Well, if we had that, we could actually design this pretty simple procedure. We could repeatedly ask the model to generate a solution and then generate an answer, and then just stop if the oracle says the answer is correct or not. And then you can just keep running this forever until you eventually get a correct answer. And it turns out if you do this with actual language models, you can have this huge impact on the number of problems that are solved. So this is showing for a variety of models what happens if you run this procedure with more and more generations. And you can see that some of the models are actually getting to 100% on this kind of difficult math benchmark. Now I know what you're thinking. We don't usually have this oracle that tells us whether things are good or not. And probably the strategy that I described on the previous slide is like the first thing you would think of. It's maybe the most naive kind of strategy you could use. And so in fact, there have been other ways and other strategies developed, and we formalize these using the term meta generation. So a meta generator takes in some input x, and then it'll also take in these sub-generators that it's kind of calling to generate sequences. And then it takes in other parameters, like other models, like a reward model, as well as the number of tokens or number of sequences that you want to generate. And then the algorithm itself will design some strategy for combining all of these things, such as the one we just saw on the previous slide. And you can kind of see that the previous algorithms are a kind of special case where you just provide the algorithm with a language model. Your strategies are things like, which sampling adapter should you use beam search or not? And your parameters are things like temperature and beam width. So we're going to go over 4 different higher level strategies that have been developed. These are called chaining, parallel generation, tree search, and refinement or self-correction. And then I'll briefly talk about scaling meta-generators, and in particular, like how you can choose a good configuration for a compute budget that you have. So the first pattern, called chaining, is kind of simple and intuitive. You basically take a generator, create some intermediate output, and then call another generator, and just keep doing this until you get some final output. So a motivating example is the chain of thought method that I talked about earlier. And you can kind of view this method as being a 2-part decomposition or 2-part chain, where first we ask the generator to generate these intermediate thought tokens in green. Then we call it again to finally generate an answer to the question. And again, this might seem like kind of simple, but there's been a lot of cool work since the chain of thought came out, showing that like at an actual like pretty deep level, you can formally show that this increases the expressivity of the generation system. So some like takeaway intuitions are that like when you add in these thoughts, you now enable this output length that is variable. And you can think of this as being similar to a tape in a Turing machine or a form of memory that the model now has access to. You could also think of this, again, as this 2-part decomposition, and then think about, like, what if you had more steps, or if you incorporated some external tool. So here's an example of that called self-ask. And they essentially frame generation as they first generate this query, then they call an external tool, so in this case a search engine. The search engine comes back with a response, and then you can repeat the process and eventually get an answer at the end. You can kind of view these sequential meta-generators as a kind of program where the outer level program is your meta-generator, and then your inner level calls to tools and things like that are these inner functions of the program. And this idea has actually come up in several different ways in the literature. So here's showing one called demonstrate search predict programs. It's also known as language model cascades, LLM programs, and yeah, so this idea pops up in different places. And then you could imagine, like, for whatever you're trying to solve, you could design one of these chains. So it could be everything from rewriting an input before you perform your final generation. Or here's one from our work where we were generating these verified formal proofs, and we broke it apart into a kind of 3-step process. Okay, so chaining gives you this really natural way of decomposing generation and incorporating calls to like external functions or external tools or models. But if you kind of think about it, if you just run one of these chains once, then it's not really exploring the space of possible outputs. And so that kind of motivates the next meta-generation pattern that I'll talk about, which is called parallel generation. So parallel generation, again, fairly simple idea. You have your generator, and now you call it, and instead of just generating one output, you generate n outputs. Then you have some function which you call the aggregator, and that takes in these n outputs and produces the final output of the system. So these methods will vary based on your choice of the aggregator. And I'll tell you about 2 that are really common and actually really effective in practice. So the first option is to just take the maximum. So here you assume that you have this reward model, and the reward model gives you a score for each output sequence. So like, this one says 2 plus 2 equals 5, so hopefully our reward model gives that a low score. This one says 2 plus 2 equals 4, so it gets a high score. And then we just take the maximum, and that's the output. And so this goes by the name of best of n, or rejection sampling. And you can probably see that a really key part of it is this reward model. So let me just give you some flavor of how you would train one of these reward models. Let's say you're solving these math problems, then what you can do is you can generate a bunch of solutions, save the ones that have the correct answer and ones that have the incorrect answer, and then you essentially just train a classifier to classify whether a given output is correct or not. Sometimes you only have this preference-based data, so you only know that one sequence is preferred over the other. You don't really have a notion of correctness. So you can also train a reward model to assign high scores to things that are preferred and lower ones to things that aren't as preferred. And so training the reward model obviously has a lot of details and itself is a really interesting active area of research. So I'm not going to go into further details here, but hopefully this gives you some flavor of where this reward model comes from, because it will be used in the later methods as well. So why would you want to do this best of n procedure? It's kind of cool. In some sense, what it's doing is it's approximating the search for the most acceptable sequence. And you can see this through this like two-step argument. So in the first step, we're saying that by using n sequences, we're approximating the maximization over all possible sequences. And this is really good because this approximation will get better as you increase the number of samples, so as you scale up your inference compute. Then in the second step, we can actually run into issues because what it's saying is that our reward model is actually approximating your notion of acceptability. And so what can happen is that the best of n can actually find outputs that get really high reward model scores, but aren't actually kind of good outputs. And you can see this in practice, and it could be kind of striking. So here's a really cool paper, one of the early papers doing this for the math problems. And so you can see as they increase the number of generations on the x-axis, their solve rate is going up, which is good. But then eventually the best of n starts finding these outputs that are getting high scores from their reward model, but they aren't actually correct solutions to the mathematical problems. So another thing you could do is to use a different type of aggregation. And so another common one that's used is majority voting. It's also called self-consistency. And here again, the idea is really intuitive. So let's say we're solving math problems. Then we generate this initial sequence, which is like a reasoning path, and then we end in some answer. And then majority voting says basically return the answer that occurs the most often. So really kind of intuitive idea. Then you can incorporate your reward model into the majority voting. So what you can do is basically weight each vote by the reward model score. And so this is nice because it can break ties, like in the example here. If you have a really good reward model, it can also kind of favorably bias the voting procedure so that you can do a bit better than if you just don't have the reward model. So in practice, these kinds of methods can have a huge impact on performance. Here's an example on this mathematical reasoning benchmark. And you can see that as the number of generations is being scaled up on the x-axis, the solve rate is increasing. And then what's really interesting is especially as you get to these later higher inference budgets, you do see this gap opening up. So the specific strategy that you use can actually make a difference. And in particular, here this weighted voting is actually doing better than the majority voting or the best of n. So let's maybe try to think about what is this weighted voting doing and why might it be a good thing to use? And to do that, we can think about what happens if I was to send the number of generations to infinity. So if you had an infinite compute budget, what would happen? So it turns out this is kind of a cool result. You can show that the accuracy that you get with the weighted voting would converge to the accuracy that's shown here. And so let me step you through this. What it's saying is that it's the accuracy that you get if you were to sum over or marginalize out these intermediate reasoning paths before the final answer. And so this is a really nice intuition. It's essentially saying that like the weighted voting is taking into account all of the different paths that your model has to getting to a particular answer. And then you can also like stare at this for a bit and get kind of three nice takeaways. So one question is like, if we keep generating more and more, will we kind of solve everything? In general, unfortunately not, because this result is basically saying we'll converge to this accuracy that's shown here. Second, you can see when weighted voting is better than voting. And it's essentially when your reward model is kind of slightly better than your generator at assigning mass to solutions that have correct answers. Oops. And then the third one is like, how can we possibly keep improving performance? Well, if you look at it, there's kind of two options. You can improve the performance of your reward model, and or you can improve the underlying generator that's generating these candidates. And so we'll see in the next part how we can design a meta generator that actually causes majority voting to do better. But let me just briefly comment on this, the reward model. So this itself is a very active and really interesting area of research. Here's a kind of fun example where they improve the reward model by actually using the techniques that I just told you about. So they use this chain of thought reasoning, they use parallel sampling, and then they use this aggregation at the end. And so it's kind of meta in the sense that like they're using these techniques to improve the reward model, and then you could use that reward model within the majority voting itself. So the parallel meta generators give you some way of exploring the space of outputs by generating full sequences. And in practice, this can actually lead to really large performance gains. However, these methods are ultimately bounded by the quality of your evaluator and the generator model. So one insight is that you only use your reward model or your verifier kind of at the very end. And so possibly can we do better by somehow leveraging the reward model at kind of intermediate stages of generation. And that motivates the next methods, which are based on tree search. So tree search assumes that you decompose your generation process into this search over like states and transitions. So in the case of the math problems, you might call your generator to give you multiple options for the first step of the solution. Then you come up with some way, and I'll tell you in a bit how, of coming up with scores for each one of these states. And then once you have the scores, you can like run a tree search algorithm to say, you know, pick the one with the highest score, choose that one to expand next, and eventually get some full output. So in general, if you're going to try using tree search, you have to think about what are your states, what does it mean to transition from one state to the next, and then how do you get these scores, and then what actual like search algorithm are you using. So let's look at a concrete example with the math problems again. So here we're going to generate one step of the solution at a time, and so our transitions are going to be pretty simple. We're basically just going to like append the next step to the previous steps and move through the tree in that way. So one key question is like, how do we score each node of the tree? And so for that, you can use what's called a process-based reward model. So the reason it's called process-based is instead of taking in the full solution, it'll just take in the solution generated so far, and then it's essentially trained to predict whether the solution is eventually correct. So you can see this as being like the expected return from your current state. And you can train these in different ways. So you could have humans try to annotate, is this step correct or not? And this is done in some papers. Or you can actually generate a bunch with your model and get some approximation of, whether the solution will eventually be correct from this current state that you're at. So then you have to design some tree search procedure for incorporating these scores. Here's one that we designed recently, and it's called reward balanced search. And it uses a really intuitive idea. So it basically takes the scores that you get from your reward model. And then the question is how do you decide what to explore next when you're doing the tree search? And so what it says is you want to allocate your exploration budget according to your reward model scores. So concretely, we look at the current search frontier, take the softmax of the scores, and then you can decide, you can use those to kind of allocate this budget. So in this case, this one got a low score, so you wouldn't explore it at all. This one had this, 2 + 2 = 4, so maybe you explore it a bit more. This one we're not really sure about, so we allocate some exploration budget to it, but not too much. Then you can actually incorporate the tree search into majority voting. You basically run the tree search, get n different outputs, and then take the majority answer. And so the key idea here is that unlike parallel sampling, the tree search can use these intermediate scores, on individual steps. And so possibly it could do a bit better. So it is possible to get better performance with the tree search. Here's one example where even if you adjust for the amount of compute that you're using, so same number of generations, that's on the x-axis. You can see here that the test error, so lower is better, is actually better with this tree search algorithm versus using the parallel sampling. And so aside from these math word problems, we do see tree search coming up in different domains. So a famous one that didn't necessarily use language models is Go. So tree search was a kind of key part of AlphaGo and the later variants. In formal theorem proving, which today does use language models, essentially any state-of-the-art system will use a tree search at inference time. The reason there is that you have this formal proof assistant, and essentially after each step of generation, the proof assistant will give you new information. And so if your search algorithm kind of takes advantage of this intermediate information, you can do a lot better than just generating the proof in one shot. And then similarly, in some of these more recent agent environments, you often have an environment that you're interacting with. And so every time you kind of take an action, the environment will give you new information. And so this again gives you some opportunity of exploiting these kind of intermediate states to perform some kind of tree search. And in fact, we've seen some papers starting to explore this. So the tree search meta generators, they can backtrack and explore using these intermediate scores. However, if you're going to use tree search in your problem, it is worth thinking about actually whether tree search is a good fit. So in particular, you really want your generation to decompose into these kind of multiple states. Ideally, you want an environment which is giving you extra information at each state. And then you really want a good reward signal so that you can train this really good scoring function for performing the tree search. So the final meta generation pattern that I'll talk about is called refinement or self-correction. So here, the idea again is very kind of simple. Let's say that we're generating and we make a mistake, or we go down some kind of bad generation path, like we generate 2 + 2 = 5. Then a refinement or self-correction method will try to produce a path that's kind of better. So maybe it corrects this into 2 + 2 = 4. It turns out that there's several ways you can think about designing a system like this. One way is to actually assume that you have some additional module that gives you feedback. So like, what if we had some module which said that 2 + 2 = 5 is wrong? Then it seems like performing the correction might be, a bit easier. And as you might imagine, the quality and where you get this feedback can be incredibly important. And so you can think about the feedback in kind of two different categories. One is whether you have kind of external information at generation time. Those are called extrinsic methods. The other is if you try to build one of these refinement or self-correction systems using just a single model. So you're just like reprompting it to maybe like give its own feedback and then regenerate. So a really classic example of the extrinsic feedback is in code generation. So here's an example from one of our recent papers that incorporates a program verifier into generation. So in particular, for some of these Rust programs, you can actually get this formal verifier, which tells you whether your program is correct or not. And then it can also give you these kind of detailed error messages that can sometimes even localize the error. So then what we do is we feed back in the output of this verifier to a corrector, which is an LLM. And then hopefully the model generates some improved program. And of course, you can just like keep running it longer and longer until you eventually find some verified program. And doing this can have a huge impact on the number of programs that you're able to successfully generate. So here's showing what happens if you just keep running this like parallel generation without any refinement for longer and longer. And you can see that the system is able to like do some of this verified programming, but then eventually it just reaches its kind of capabilities limit. Then if you start out with 256 generations and start doing refinement, then you can get this additional jump in performance that you otherwise can't get, without the feedback. So how you do the refinement, there's different ways, and you have different design choices, so you can check out the paper here. But the high-level takeaway is that, like, if you have these external sources of feedback, you can often get benefits with these refinement methods. We also have some tutorial code demo where we have a simplified version of this that you can check out. So yeah, this idea comes up in other areas like code interpreters, incorporating a retrieval model, or Graham Newbig, who's on the tutorial team, has a kind of fun tweet where he does this kind of interactive refinement with an agent and is able to do better than the O1 model for like generating a summary of a paper. So the other extreme is to just have a kind of fully self-contained refinement system. So here what you would do is you would prompt your model to provide feedback on the output, and then you would send that feedback back into the same model and try to produce a better one. So this, at least so far, has had results that are more mixed. It's more nuanced. So in general, like with tasks that are easy for the model to evaluate, like let's say it gets 9 out of 10 citations and has to just like refine the output to include one more, then these kind of intrinsic refinement methods have been pretty good. In terms of expanding the underlying kind of reasoning capability of the system, this is a more active area of research, and the results are sometimes more mixed. So here's an example where, they essentially show that like if you use GPT 3.5 to do this self-refinement, then it would just as often go from a correct to an incorrect solution as it would from an incorrect to a correct solution. So in some sense, it was having trouble kind of evaluating the correctness of its own outputs. So here's a kind of fun toy example. We might not have time to like fully go into the details here, but you can basically simulate this idea of having noisy feedback and basically control the performance of one of these refinement systems. So here we're using a really simple language model that just generates one character independently of all the other ones. And then let's say you have a oracle feedback which tells you exactly which characters are incorrect. Then if you have this, you can build a refinement system that can actually perfectly generate this output sequence. And then based on how much noise you add to the feedback stage, you can basically adjust the performance of the refinement system. So intuitively, like when these language models might be failing to do the self-refinement, maybe it's that they look like this green curve down here, where their kind of own feedback on their own generations is just too noisy to do anything meaningful with. A third case is to just discard the feedback module altogether. And so here the goal is to actually train a model to directly learn to correct outputs. So why might this be possible? Well, you could imagine like if you're training this with some kind of reinforcement learning, where the model is encountering all these different examples of like going from a worse output to a better output, then these language models are pretty flexible. Maybe there is some hope of learning this kind of correction behavior. So there's been a few different attempts at doing this, and they usually take the following form. So you collect these bad and then better pairs by generating and then ranking them using some reward function. Then you train this corrector model to generate a better output given the bad one. And then you repeat the process. So it like keeps training online and hopefully improves over time. It turns out that doing this, it can be difficult to get this to work. And there's a really cool paper called SCORE, which shows that sometimes the corrector can actually have these degeneracies. So for instance, like it can just completely ignore the intermediate output and in some sense learn to just solve the problem. But they were able to overcome it with some specific reinforcement learning and regularization techniques and get this kind of promising result where you could see as the number of generations is scaled up, their self-correction or sequential method is actually doing better than the parallel sampling. So in summary, the refinement or self-correction will depend a lot on whether you have this kind of external source of feedback and if you're trying to train the model to directly correct. If you do have this extrinsic high-quality source, then like as a first approximation, it's probably promising. For the intrinsic methods, it's more of an open question. And then if you're trying to train a method to self-correct, this is also a very active kind of open question to get a model that's trained to self-correct in a very kind of general setting. So those are the four key patterns or strategies that have kind of emerged for these meta-generators. Let me just briefly talk about some aspects of scaling meta-generators. So one aspect is, I've talked about all these different strategies, but how do you actually choose a particular meta-generator in practice? Well, a really important thing to notice is that like all of these involve generating many, many times with models. And so a really important thing to take into consideration is the cost of the meta-generator. So you can think about the cost being dependent on the size of the model you have, as well as the number of generated tokens that you're doing to get an output. And so you can kind of formalize this as the problem of compute optimal inference, where you have some compute budget, and you want to choose the configuration, so the number of model parameters, the number of generated tokens, and the inference strategy that gives you the best performance, so the lowest error, subject to your compute budget. And then once you have this problem set up, you can try to come up with these different curves that look like this. And if you've seen these kind of scaling curves for pre-training, they start to look somewhat similar. So here you have this compute budget on the x-axis, and then what you can do is try various different configurations. So for instance, you can take different model sizes and then scale up their inference budget, and then at each point evaluate how well they're doing on some task. And then what your goal is to get something which is on this compute optimal frontier. So you want, like, for a given budget, to select the configuration that has the lowest error or best performance. So an example question you can ask is, like, is a smaller model and generating more actually better than using a larger model and generating less if I have the same compute budget? And so you can actually create one of these curves empirically. And here's an example one. So this is showing on the x-axis the compute budget in terms of the flops that are used at inference. Then each colored line is a different model size. And then on the y-axis, we see the performance on this benchmark. And it's pretty cool because it's basically saying that, like, okay, let's say you have this medium-sized compute budget. Then it's actually more optimal to use this medium-sized model and maybe generate more than to use the larger 12 billion parameter model. On the other hand, at least in this case, if you want to get the lowest possible test error, it does appear beneficial to just, like, spend as much compute as you can. So use the largest model you have and then keep generating if you're not compute constrained. You could also try to vary the meta generation strategy additionally. So here this is also varying whether we're using sampling, this kind of expensive tree search, Monte Carlo tree search, or the rebase algorithm that I told you about. And here you can, again, get this kind of cool result, which is, like, the meta generation strategy that you use can actually have a big impact on the compute optimal configuration. So in particular, in this case, using this tree search algorithm turned out to be compute optimal across all the different inference budgets that were tested. So for example, if you have a small inference budget, you would use the tree search with 7 billion parameter model. If you have a larger inference budget, you would use the larger model and with the tree search. So zooming back out, what this is kind of saying is that performance with these meta generators can improve with with increased compute, but then it can still vary based on the strategy that you're using or the size of the model that you have. And so in particular, like, if you have a certain compute budget, you want to decide, like, what is the best configuration for your inference setting. And so sometimes smaller models can actually be better for some budgets. And ultimately, we would want some strategy where you kind of don't have to worry about this, and it's just always optimal for all budgets. So to recap, I talked about meta generators, which are kind of higher level strategies for calling generators and incorporating external information. I talked about 4 different patterns, and these patterns can also be combined and mixed together. And in general, we want to choose and design methods that both give us good task performance, but then also, we need to take account the inference cost, because inherently these methods involve, potentially generating a lot. And so on that note, next, Haley will tell us about another aspect where we don't just look at the token budget that we have, but we actually look, like, at a systems level, whether we can use techniques to speed up the generation or the meta generation, and in turn make these methods more scalable and more useful in practice. So with that, I'll hand it off to Haley for the section on efficient meta generation.
Great, yeah, thanks so much, Sean, for that intro. So as mentioned, before we've talked about sort of how generators work and how to stitch them together into more complex programs in the form of meta generators. In this section, I'm going to talk about how that maps onto actual real-world efficiency. There's sort of a lot to cover in this area, so I'm going to try and tightly scope it to the relation to meta generation. I'm going to do this by first going over some of the basics of how we make language model inference efficient, then talk about how this maps onto making meta generation specifically faster, and what this means for the interaction between meta generator algorithmic design and efficiency. So first off, when I say efficiency, what exactly does this mean? Two metrics that often come up are first latency, which measures basically for a given user submitting an input to some language model API or instance, how long they wait to get a response fully formed out. Or throughput, which measures the volume that a system can serve in terms of something like 20 requests per second are returns to a user in aggregate. There are other metrics as well that people use, like time to first token, but we won't cover that here because that's not as well suited for meta generators, which don't just generate one token autoregressively at a time. Importantly, latency and throughput often, but not always, are at odds with each other, and often also trade off against model quality. For example, we can imagine that a language model that arbitrarily returns the empty string upon every user input would be easy to serve with minimal latency and maximal throughput. But for a given model, like say Llama 370 billion, we'll have limitations based on our hardware of how many requests we can serve and, given the volume of requests, how much latency we can tolerate. Another thing that I'm going to bring up, which might not be controversial to people who've worked with optimizing LLM inference from the systems perspective, is the importance of hardware to serving these models. Over the past decade plus, GPUs and other ML accelerators have gotten way, way better. And the way that one achieves sort of a maximally efficient system is by respecting these hardware designs and choosing optimizations which take advantage of the hardware's strengths while avoiding other pitfalls related to the hardware. So a few key quantities to keep in mind about machine learning accelerators like GPUs that impact inference efficiency include the total amount of memory we have per device, measured in gigabytes, termed VRAM or HBM, high bandwidth memory, the actual compute capability of the device, how many operations per second it can perform at maximum, measured in flops per second, floating point operations, and another factor, memory bandwidth, measured in gigabytes per second, which represents sort of how long it takes to shuttle operands around the chip. When we want to perform a matrix multiplication, our inputs will be stored in the global device memory in VRAM, but we'll actually have to send them to the processor cores to perform computation and send the output back to device memory. These quantities come up in many ways when we're trying to perform LLM inference, such as memory bandwidth coming up when we want to load model weights from memory for performing matrix multiplications, or loading activations. The actual compute capability of the device coming up when we want to leverage our flops per second to perform matrix multiplications, and other factors like communication speeds across multiple devices when we're serving larger models. So a simplistic view of how these different accelerator quantities trade off against each other is to measure the amount of time taken for a single step of LLM inference, such as performing a ReLU nonlinearity or performing a matrix multiplication in our feed-forward layer. Here, the time that a single operation takes will be determined via the maximum of either how many floating point operations this step takes divided by how many floating point operations per second we can deliver, or the amount of data that must be transferred around the chip divided by how fast we can transfer that data. And depending on which one of these rules the maximum, will either, if the flops factor is what is larger, then operations will be called compute bounds, meaning that if we had a higher compute capability, we could perform the operation faster, or our memory bounds, in that if we could transfer data around the chip faster, the operation would become speedier. So keeping this sort of memory bound versus compute bound distinction in mind, one fundamental optimization performed in LLM inference is batching, in which instead of just running a single input through the model at a time, we stitch together B different input vectors and pass them through a model all at once, achieving inference on a single batch altogether. Often our weight matrix will be much larger in size than our input activations at a small batch size, and so the memory bandwidth cost of loading the weights from memory is much larger than loading these inputs from memory. What this means is that when we have a large batch, we only load this weight matrix into memory a single time. And if the operation is memory bound, then even though we're performing more operations to use a larger batch size, we might still see a constant amount of time that this operation takes to perform, since we're sort of amortizing this loading of the weight matrix. However, when we have a large batch size, this might change to a compute-bound regime. Another core concept in LLM inference is KV caching. Inference is typically structured in two stages. First is a prompt processing stage called prefill, in which, given sort of an n token prompt, we'll perform attention using all n tokens, and then save these key and value vectors computed over the course of attention for later. Then, when we want to generate a new token from our model after we've already processed the prompts, we perform something called the decode stage, in which we've retained the key and value vectors from attention of our prompts and the prior generated tokens, and we only have to compute the new query, key, and value vectors for this single new token at once, and perform attention for this new query token. This KV cache can actually become quite large at large batch sizes, and its size is determined by the number of key or value vectors that we're storing, measured in terms of the context length times the batch size, a sort of model inherent size factor measured in terms of 2, because we have both a key and a value vector that we're storing, times the number of layers, since we have to store this cache for each layer in our model, times the number of attention heads times the dimension per head, which measures the width of our model, as well as a factor of the number of bytes per element in these vectors, 2, for example, if we're storing these in 16-bit. With these sort of basics in mind, let's think about how we might speed up a single sort of sampling of a token, the decode stage. Here we'll want to work around our sort of hardware bottlenecks, typically. Again, coming in the form of either memory bandwidth, the total compute capability or flops per second our device can deliver, and the total number of operations we have to perform. In terms of working around memory bandwidth bottlenecks, we do this by reducing the amount of data transferred around the chip. The typical amount of data that we have to transfer during a single inference step is on the order of the total number of parameters that must be loaded in from memory in the model, times the size of each parameter value in bytes. So one option is to reduce this bytes per parameter factor by quantizing, in which we take our floating point values in the weights or activations and bucket them into a smaller storage size data type, like int4, for example. Another option is to also compress or distill the model to reduce the factor of the total number of parameters that we have to load while keeping the bytes constant via, for example, dropping a layer from the model and training further, otherwise distilling it or compressing it in other ways, and so on. Another way to improve single token decoding efficiency is to maximize our utilization of the device's compute capability, improving the hardware utilization. One key example of this is flash attention, in which, although flash attention performs the same logical operations that regular vanilla attention does, by optimizing the implementation in a single kernel that reduces memory loads, it performs it using a far greater number of flops per second effectively, and completes it in a lower amount of time. So although the total number of flops that we must perform for a given decoding step remains the same, the number of flops per second that we execute increases, reducing the time. Finally, we can reduce the absolute number of operations that are required in general. One example of this is mixture of experts models, in which instead of having one single large feed-forward layer, we split the feed-forward layer into a number of different chunks called experts, where each token will only activate one or a couple of these experts, using many fewer flops than it would if it passed through every single expert. Now we're going to think a little bit about how we can speed up a single generator call, where we might generate n tokens from a given input. One key observation here is that when we're generating n tokens from a language model for very large n, a key bottleneck here is that we can only generate the next token n plus 1 after we've generated token n. However, some tokens might be easier to predict than others intuitively. For example, when we're generating punctuation, this might be very easy for a weak model to guess that the next token is a period, whereas other sort of structural elements might be trickier. So is there any way that we can spend less time on these easier tokens like punctuation, much like we did with constraints generation? One option here is speculative decoding. In speculative decoding, we maintain our main target model that we want to generate from, and also initialize a much smaller and more efficient draft model. At each step, instead of just sampling a single token from our large model, we'll first generate n tokens using our draft model that we treat as guesses for what our large model might produce. We'll then feed these n tokens from the draft model into our larger model, and in parallel, much like a small prefill stage, get the logits for our model across all of these n guesses. Then we'll iterate through these guesses, starting from the first one and going forward, determining whether they match up with what our larger model would have predicted if we just asked it to produce one token. Until we get to the point where one of our guesses doesn't line up, we can accept all of the preceding guess tokens and ideally in expectation generate many more than one token per step through our large model. Because our large model is large in size and its weights take a lot of memory to store and load in, the decoding step is typically memory bound, and so passing in n guess tokens can take the same amount of time as just passing in a single new token. I'll gloss over this for now, but we also have a code example of speculative decoding in our repository. So definitely check that out if you're interested in how speculative decoding not only operates, but also maintains the output distribution of the larger model. Another core thing about speculative decoding, however, is that its efficiency is variable. For example, on easier distributions, where a small draft model can more frequently guess the correct token, we can get a larger acceptance rate of these guesses and a higher efficiency as compared to a harder distribution. Another factor in speculative decoding is that it's often helpful for latency in cases where we only have a batch size of 1 or a very small batch size. Reducing the number of calls to our larger model and the number of times we have to load its weights from memory can speed things up massively. But when we have to optimize an inference setting for throughput, speculative decoding can hurt this, even if it improves latency. However, recent work called MagicDeek has shown that because the KV cache is so large and so costly to load from memory at each step, when we have a long context length, like for example 16,000, speculative decoding not only can help latency, but it can also increase the throughput quite significantly. So now let's come to how these efficiency techniques and basics map onto speeding up the meta generators that we've talked about previously. In particular here, again, we're interested in how these meta generator algorithms interact with sort of real world wall clock time and utilization of our accelerators. And we'd like to answer questions like which sort of algorithmic patterns for meta generators are the fastest, and also use this to inform designing more efficient meta generators in future. One key pattern that pops up, especially in parallel meta generators, but across many different algorithms, is the existence of a shared prefix content in these sort of inputs, in the sort of calls to our language model generators. In this setting, for example, when we have ChatGPT with a long system prompt and many different user requests, all of which are stuck onto the end of this system prompt, this system prompt basically remains unchanging, and because language models are autoregressive, its like KV cache vectors are unaffected by whatever might follow it. And so this shared prefix doesn't necessarily have to be processed by our language model every time. One way to take advantage of this is via page detention introduced in the VLLM library, in which when we have a sort of consistent shared prefix that we use across many different language model calls, we can map this shared prefix across many different logical requests onto the same specific physical block in GPU memory whenever possible. This helps a lot because it means that we can store a larger batch size on the same GPU, but we might want to do better. Another thing that can happen as well is that we can have a sort of structure in our requests to our language models beyond just a single level of a shared prefix. For example, this figure shows what we might have if we have both a long few-shot prompt plus many different sort of questions, user queries or questions we might want the model to answer, and then we perform best of n or majority voting for each question that we feed into the model. Here we have sort of two tiers of shared prefix content, and we'd like to leverage this as well. Methods like radix attention, introduced in SGLang, deal with this by setting up a sort of tree structure of KV cache blocks, mapping sort of the dependency of which thing precedes which other thing, and holds this as a tree which eventually maps onto physical GPU memory, only evicting sort of leaves of the tree when they're not used enough and more GPU memory storage is needed. However, the optimizations like the previous one, which allow a bigger batch size by reducing GPU memory overhead, aren't all we can do. A paper called Hydrogen from Jarafsky et al. Improves the actual speed at which we can compute attention on these sort of shared prefixes like system prompts by noting that not only can we store the KV cache for this shared prefix in memory a single time, but we can also only load it into the GPU processors a single time. And also cast this as a matrix-matrix multiplication rather than many matrix-vector multiplications with the same matrix. Because GPUs are optimized so heavily for matrix multiplication, we get huge speedups from modern hardware by doing this matrix-matrix form of prefix attention. What this allows is for massive throughput increases, especially at large batch sizes, all of which share the same long prefix, as seen by this comparison of VLLM speed versus hydrogen speed. But also, the speed when using hydrogen almost competes with this blue line, which is sort of the upper bounds in speed if we spent 0 time at all on the actual attention operation. What this means is that attention on sort of a shared prefix that we reuse frequently, like a few-shot prompt or system prompt, is very, very cheap, almost to the point of being free. Now, going back to dig deeper onto this idea of reducing the memory that the KV cache uses beyond just shared prefix settings, how can we sort of reduce the KV cache size even when we are not able to do this via using shared prefix structure? One option is something called token dropping, which acts on the number of KV vectors that we store. For each input in a batch, token dropping or eviction approaches look at the statistics of attention on the previous tokens in the prefix. And whenever a token is judged via some heuristic or algorithm to be unimportant in that new tokens we generate often do not attend to it, we evict it from the KV cache, no longer storing it in memory. This has some downsides in that maybe if we evict the wrong tokens from memory and change the topic of our conversation with the model, or we just sort of try to evict too many tokens, then our generation might become brittle or unable to refer ever to these new dropped tokens again since we've gotten rid of their KV vectors, but can keep KV cache, especially for a long context length, in check. Another option is to act on the data type of the KV cache by reducing this number of bytes per vector element factor. Again, we can use quantization, where we take the floating point elements of our KV cache vectors and map them into a lower bit width data type to reduce storage. This can allow us to, again, store more KV cache vectors on a given GPU and fit a larger batch, increasing throughput. Finally, we can act on the sort of model inherence factor of KV cache size by reducing, for a given model size, how large its KV cache state will be. This is typically done via architectures like multi-query attention or grouped query attention, in which instead of typical attention where we have the same number of key and value heads as with query heads, we reduce the number of key and value heads and share them across these queries. Thus, even though our model has approximately the same number of parameters, the actual number of KV vectors that we need to store for a long sequence is drastically reduced. Now, to recap what we've covered and think about which meta generators are the most efficient, The ones that are most efficient are ones that have a parallel pattern where we can run, if we're running sort of n trajectories and calls to a language model, we can do all n in parallel and not sequentially bottleneck our generation speed via sort of waiting for the results of one call to perform another call based on it. And also generations which are prefix shareable, where if we do have some sort of like long state or input to our model, it's viewed as sort of a static long input where we have the same system prompt or RAG retrieved context in the same order or same long few shot examples presented to the model across calls, where within a batch we can just reuse this encoded state across the prompt and generate these calls much faster than we could otherwise. And so in conclusion, if we want to sort of holistically view meta-generator efficiency and decide which algorithms are the fastest, we have to look a little bit deeper than token budget and think about sort of what the program structure is and how to set up these meta-generation algorithms. And I guess one very surprising insight is that prefix shareability means that meta-generator efficiency depends on the structure of your prompts, which seems quite surprising a priori. Cool. Yeah, now Sean will be taking it away for some recap.
Okay, thanks everyone for your attention. It's awesome to see everyone here. So just as a recap of some things we've talked about today, it looks like we'll have a few minutes to do a Q&A and then a panel session. But first, yeah, let's look at what we talked about. So the tutorial was on these algorithms called meta-generation algorithms. And we started out by looking at how you just generate kind of one token at a time to do something like implement the LLM APIs or LLM inference libraries that you might be familiar with. Then we looked at some higher level patterns for calling these generators repeatedly and incorporating external information. So that might be a reward model, it might be some external tool, or things like that. And then finally, Haley just talked about strategies for efficient generation and meta-generation, which are really critical for scaling these methods up or deploying them in basically any setting that you have. So some takeaways are, so far there's been different patterns that have emerged for these meta-generators, and each one is kind of turned into its own sub-area of research. And so some of these patterns we're beginning to understand better and better. And one common theme is that often we can kind of spend test time compute to improve the task performance that we have. And then when we want to either design a new meta-generator or choose one for our task or our deployment setting, we want to take into account not just the task performance, but also the cost, because these do involve, kind of by their nature, potentially spending a lot of inference time compute. In terms of efficient meta-generation, we saw this kind of core idea of leveraging different forms of parallelism in order to decrease the latency and boost the throughput of the system. And then one key idea that kind of kept showing up is figuring out kind of clever ways of exploiting the fact that you have these shared prefixes. So a simple case is, you're doing best of n and your prompt is shared. But then even, recent methods support these kind of more diverse topologies like a tree search, where you do have this shared structure in some of the search paths. And then, as Haley mentioned, at the kind of systems level, the optimizations that you have can actually make some meta-generators more feasible or less costly than others. So sometimes just looking at the token budget could be useful. Like let's say you're comparing best of n and refinement, and you just use the token budget and it's fine. But then if you're really looking to do an exact comparison of the runtime of your system, this token budget can often be an oversimplification due to the underlying optimizations that you have. So I think this area of LLM inference and meta generation really has a lot of exciting research going on, as well as some outgoing paths. One thing that I think we'll see a lot of is combining some of these kind of primitives that I talked about, so things like refinement, parallel sampling, tree search, into these kind of hybrid systems. So here's an example of a paper that I mentioned earlier. Well, it was actually just released today. And we combine parallel sampling and refinement and tree search into a kind of single algorithm that gives us pretty good performance on this verified code generation task. And then there's a lot of other really exciting directions, and I think we'll discuss a lot of them in the panel session today. One is kind of thought-provoking. It's like, I've been telling you about these different search algorithms, but could you actually have a system that just learns to search on its own? And then at inference time, you use a fairly simple algorithm, like you just ask it to just keep generating and searching on its own. And how you enable that is kind of an active area that a lot of people are interested in. Another are these agent environments that I mentioned earlier. So these are really cool because, you know, every time your agent takes some action, then you could potentially get a lot of information from the environment. And then oftentimes we kind of train a system and then, you know, try to use it as an agent. And so figuring out what the right patterns are and how we can kind of leverage things like search and what auxiliary models we need to train for these agent environments is a really exciting and interesting direction. And then finally, just broadly, there's a lot of open questions on just how we should best allocate compute. I started off the talk by talking about, you know, pre-training compute, post-training compute, and test time compute. And how all of these things interact is really still being figured out. And then at a very fine-grained level, like I talked about these compute optimal meta generators, but really we want to go even more specific. We might want to say, like, for a given input, what strategy should we use, or how much compute should we spend on this input, and basically everything in between. And then I should say that many of the conclusions that we draw about different methods and strategies are often based on just you know, a small number of tasks. And so just testing these out and investigating wider distribution of tasks is also incredibly important for scientific and practical reasons. So as I mentioned, all of the content of this tutorial was derived from the survey paper that was just published at TMLR. So you can check it out here if you want some additional reading. And you can also check out our webpage, which, as I mentioned, has all of the information related to the tutorial. So we have all the slides there. We have additional code. Many of the code snippets we didn't even have time to present here. So you can check those out for further study and a deeper understanding. In addition to the survey paper, we also list the papers that were mentioned in the slides, so you can quickly see a kind of relevant reading list if you want to look deeper into the specific topics. All of us are also accessible by email, and many of us are here at NeurIPS. So all of us love talking about all of this stuff, so do find us throughout the conference. Feel free to send us questions that you have. With that, we do have a bit of time before our panel session. So we'll start the panel session at 3:30. So we'll have 30 minutes. And we have this amazing group of panelists. And we have Ilya from the tutorial team, who is at Meta AI as moderator. I'll let Ilya actually introduce the panelists, but in the meantime, for the next 14 minutes, we're happy to take, any of us are happy to take questions that you have. And I think to maximize the time with the panelists, we'll stop right before 3:30. So thank you so much for your attention, and do stick around for the panel because it's going to be awesome.
We're going to host our panel session now. So while they take seats, let me introduce our participants. Betty from CMU, she's going to present some views on these recent libraries like SGLang she has been working on. Nuha from AI2, Rishab, Jacob, and Noam. So Rishab is from DeepMind and McGill, Jacob from Oxford and Meta AI, and Noam Brown from OpenAI. And I'm from Meta AI. I do some research at FAIR. So can we get some mic check with you folks?
Hello.
Okay, that's great. I think we'll go over some questions and we'll try to get all the discussion from participants. The first one is about tooling and usability. So there has been a lot of excitement progress on inference-related tooling, and the progress has unlocked the ability to design new algorithms. For instance, SGLang makes using a tree search more feasible, while several other libraries allow for easily chaining together model calls in different sort of model agent, like agentic way. And moving forward, how do you see the tooling around inference and meta generation evolving? Will we see some sort of standardization of that, like a PyTorch for inference? And right now, I would like to start with Betty and Rishab, and then we go over everyone else, like everyone. Betty?
Oh, from me? Okay. Hi, I'm Betty. So we were, our group work on a particular area that is very related to this question, which is long context generation. So I guess a paradigm shift, except for test time scaling in general, is from the system level. You can see there are many open models you try, claims to have 128K or 512, this kind of sequence length, but their generation length or the quality starts to degrade. So you usually don't have this kind of request, but we know that in the test time training, I don't know if it's based on rumors or I kind of get the information, but it's kind of in the generation length, it's actually pretty long and informative. So that kind of shift this system time challenge. And for example, from the hardware perspective, we know that for usual generation, which is covered in the tutorial, that the bandwidth matters. But the long generation will make it even worse, right? Because the cable cache management on the RS is more complicated. And there are other hardware, for example, in a heterogeneous way, for example, CPU is really large on the memory size. Bandwidth is 10x slower than GPU, which is fine, because it is flops is 100 times worse, right? So there are different algorithm co-design, new opportunities here. And test and scale, no matter it's for training or for the serving. And second of all, we work on a lot of approximation and kind of a compression algorithms, which is also interesting here. So you used to just evaluate a model which is compressed or quantized sparsed with no matter it's activation-wise or the model-wise, and you see, oh, I get this benchmark of 90%, and I kind of maintain it with 88, right? You usually do it in that way. But now, if you see the repeated sampling and also changing the model, will make this scaling a little bit different. So, and sometimes you want some diversity there, which might be enforced by, for example, sparsity. So here, in this era, maybe there's a co-design between the efficiency and the ability. So I think that's a pretty interesting era for the algorithm and system, including the hardware co-design.
Thanks. That's great. And Rishabh?
So I think I'll add just one thing. So if you look at, let's say, the research on test time compute and whatnot, historically, we have focused more on optimizing single generations so that the techniques and let's say the frameworks we get are optimized for that so that we get things like speculative decoding or VLLMs. But But now, let's say we are starting to focus more on this test time compute thing. And I think in the tutorial, we presented like there are existing methods that are optimal for simple things like best of n, or let's say prefix sharing, which is really good for things like many-shot ICL. But then there is a lot of other kind of test time compute methods that are not optimized yet. And I think that's where a lot of the potential is. So to answer your question, I think there will be a lot of research and probably frameworks coming up that will be optimized for these new other methods that have not been focused on yet. But now, because of the research focus, so it's possible that some frameworks might pop up.
Yeah, I mean, very, very quickly on this. I think this will probably happen, but I think we're also at a very, very early stage of exploration. And I don't think anybody has quite understood of what is and isn't possible using test time compute, and also how what the long-term architectures will look like in terms of amortizing test time compute back into the models, when to deploy more compute, and when to just give answers. So I probably equate this not to, say, deep learning in 2015 or 16, where the first frameworks come along that are actually usable, and even then TensorFlow happened, which I think was not very usable. But something like deep learning in 1995 or 1997, when the very, very early days of the exploration. And just to give you an idea, I'm not even sure that it will make sense in the long run to think about static frameworks and static scaffoldings, because maybe the methods that we will want to use in the future, ones that actually adapt the exact structure of how they deploy test time compute and how they arrange themselves, much like we humans do. None of us operate in static core sets of exact message passings and this number of steps and this and this. We operate in flexible teams. We can readjust. We can try new things. We can adapt on the fly. So I guess I'm not convinced that we're going to stop at one level of meta generation. Maybe we're going to kick the can down the road a little bit and go meta-meta. And it's very difficult to convince myself right now that it's going to be a framework that you and I could design today, given what we know, that will be flexible enough for those new approaches. So do I think there will be something like PyTorch down the line for test time compute? Yes. Do I think that anybody would know how to design this right now to be robust to future innovations? Absolutely not.
Sounds great. So
I have one follow-up.
Oh, yeah, sure.
What do you think, at what meta level will we stop?
So I don't know. I think if you ask me in the limit, I think we will just go all the way. I think there is no sort of finite bound on metacognition for humans. I think we can really optimize ourselves quite extensively in the way that we reason our own reasoning processes and so on. And I think in the limit of compute to infinity, I do think we will not stop. We will just keep optimizing, become self-referential in the limit. So I wasn't here for the rest of the day, by the way, so in case this was covered and it's all old news, apologies, I just flew in.
All right. Yeah, I think we can move on to the next question. Thanks, just to the time constraint. And the next one will be about some of the System 2 details. Apparently, the strongest performing model right now do not operate in this vanilla left-to-right autoregressive decoding where we have a prompt and we just generate an answer right away. But that one is the most attractive one because it's so simple. And the question is, will better performing pre-trained LLMs, which means larger scale, larger data, kind of eliminate the need for such meta-generation algorithms, or eliminate the need of using multiple agents and so on in like future? Or would you bet on that? Yeah, and right now I would like to start with Anuha and Jacob, and then go for other feedback from others.
Start with you.
Hi, everyone. Great question. So about whether we need to, there is this need to eliminate the meta generation algorithm. I don't think so. Now, the question is that how do we define this very capable pre-trained language model? Now, if we're talking about a model that was already pre-trained with the same infrastructure, the same algorithm, the same post-training recipe, SFT, and then followed with an RLHF, I don't think that we will need to remove inference time algorithm. Because even though this model will be more capable with more scale data and parameter, it will suffer from the same limitation that existing language models suffer from. And there has been lots of work that show empirically and theoretically these limitations. And in my view, there are two key limitations that these systems suffer from. The first one is the snowballing of error. So one mistake that happened early on in the sequence can derail the rest of the reasoning. And the second issue is the difficulty in look-ahead task. So these large language models, they struggle with predicting the consequences of their actions several steps ahead. And so this is where meta-generation algorithms come in, and you can sort of think of them as an addition, an added layer on top of structure of search, backtracking, and evaluation. And so I see them very, very essential in enhancing the capability of large language model. Now, if you tell me that these large language models, they're more capable, but they were trained with more novel way of search, an innovative way of how to do search during training, even in this case, even though they're going to be more capable, I do think that we will still need to complement them with inference time algorithm. But in this case, I think we would need to spend much less compute at inference time compared to previous model. And why I think that it's because if the language model learn to explicitly search during training, it will learn on how to recover from mistakes and search through different options. And so at inference time, they would know how to solve problem on their own without too much reliance on inference time algorithm. Now, how I think about inference time algorithm, for me, is like a sort of a maintenance form rather than doing the heavy lifting. And so instead of generating thousands and millions of candidates to choose from, we can just be more smart about it. And you can think of it as a form of refining and extending the capabilities of these language models to their full extension. Without necessarily just exploring exhaustively the output search space. I can talk more about it, but I'll stop here.
Yeah, that's a great point. Thanks. And Jacob?
Yeah, I think there's obviously benefits to having tree-like structures that we can expand rather than having a single line of thought that we go down. Having said this, I haven't thought too deeply about if there is ever a way of flattening sort of everything into a single stream of consciousness, which I guess maybe is what I'm doing right now. I'm just decoding token by token by token, step by step, and without searching too much for whether or not this is going to make any sense. So I don't have a very good answer for you, but I think there's somebody on this podium who might be able to help us because maybe they worked on O1. So I want to pass on this question to Noam Brown.
Yeah, so I think those are two great responses. I guess the main thing I would add is that I think we're still very early in this direction, and I think that there are, O1 is one way to scale inference compute. It's not the only one, and it might not be the best one. So I think there's a lot of opportunities, especially for the academic community, to explore different ways of doing this and showing promise at small scale and showing that the trend lines look really good.
Can I have a follow-up on this quickly?
Of course.
If you were to do this as an academic, as a PhD student, how would you frame this problem so it's tractable with academic compute?
I think the way to frame it is to show that you're getting better performance as the amount of compute spent at inference time goes up. And I think that there's a lot of different ways to accomplish that, including architectural. So just showing the trend lines and I think showing promise in that, there's, I think, a lot of different ways to go about it.
And what do you think is like a minimum number of GPUs and what type you have to have so you would trust that signal of trend line going up? Do you have any intuitions around this?
I don't think there's like a hard cutoff. Certainly the more GPUs you have, the better. But I think that it is something that can be investigated at an academic budget. Because just for 30 seconds background, we had a grant at Flair Lab in Oxford on self-improvement for reasoning for LLMs. And basically, I thought this was a few months project. And turned out that my students didn't manage to make the progress we were hoping for a year and a half ago because one of them is compute in academia. Mm-hmm. So I was just curious if there is something that we can do to really try and guide the community and help academics be more effective in this space. Because I agree it's early days and would really benefit from a lot of exploration. But I'm not sure that we have the right guidance even right now in the community to do this effectively.
So anyone else want to share their thoughts? Betty or Rishabh?
I guess maybe two things. So one for the original question about the better pre-trained models, would that basically they will get rid of inference time compute. So I think what I've heard often is that you can, let's say you have a pre-trained model now and you'll have, let's say, a better pre-trained model in the future. Inference time compute lets you get a glimpse of that better model. So it seems like basically this is always going to be true for even maybe the future models, that you can always apply inference time compute, but that's what it seems like. So I guess they are complementary. And I guess to the comment from Jacob about academic and compute there, do you think the challenge there was of tasks? Because maybe in academia, what we need to do is like do all these things on small scale and then only go to larger scale when we're willing to burn the compute, rather than, let's say, trying to compete on the same kind of tasks which industry labs focus on.
Yeah, I think what's probably missing is better ideas about scaling. What experiments at small scale are indicative of progress when scaled up? And I don't think I've seen and this is quite surprising, major calls from industry labs saying, hey, these are the kind of benchmarks you have to hit at a small scale within academic compute. These are the sub-problems that we'd like to see solved. And if you do this, we'll scale it up for you. Right? So it's very surprising to me that there's this large effort across all industry labs to try and replicate O1. And no one has said, let's actually go and leverage all the talent in academia to make this a decentralized large-scale effort. And this is how you can most effectively help.
That sounds great.
Yeah, I have something to add up for these two questions. The one is we just heard about if the task actually required to look back and backtracking and not arrest, it's hard to do that. Everything in the training, sometimes you need the feedback or see what's going on to do it. Another example might be collaboration. So sometimes you need others' feedback to react, or sometimes I want to make an analogy on speculative decoding, right? So O1, or not maybe O1, but repeated sampling with reward model verification. It's a little bit similar to speculation, because you have a draft model, you just spit out, if you are decoding a tree, spitting out a lot of kind of possibilities, and you have an oracle model, which because for the speculation, your task is exactly output the distribution aligned with the original large model. But in, I guess in kind of repeated sampling with verification, this case is slightly, the objective is slightly different, but it's very similar in a systematic way. And in the speculation, I think there works, people trying to do with different small draft model, and then which you can, in the end, construct a tree or do it together and then get a better answer. So I think maybe in the Asian or collaboration, and it's very hard to embed everything in a training or rely on one model process to.
Yeah. I just want to add one thing. I do agree with all of you. And something that I want to put more emphasis on is doing search during pre-training. And why I want to mention this, because if this can be possible and if we can do it efficiently, this can be a paradigm shift in data efficiency and training very efficient models. And here I really want to quickly draw an analogy between how we human learn and how machine learns. And I know lots of people will say, come on, you can do that. Machines are different from humans, so we cannot draw this analogy. But I think let's agree to disagree today. And the way we, learn, we just, do mistakes and we receive feedbacks and we adjust and we continue learning, we adjusting and iterating. So it's just our learning is very rooted in experience. And I know that can be computationally very expensive. It's going to be algorithmically very, very expensive. But I think why not, having a model that can train over years, similar to humans, that we acquire and master skills over years and see what happens out of that.
Those are amazing points. Thanks. Let's move to the next question about the limits of inference scaling. How far will scaling up the inference time budget will take us? For instance, will it be only relevant for some tasks where we have this sort of clear verification pipeline, where things are verifiable, meaning that we can more easily kind of navigate within the search space? And will the granularity of search space scale up further? Because now we see how things go up from tokens to sentences, sometimes part of sentences. Will we see the same going for paragraphs or even to documents? And if so, then how soon that might happen? And will this depend on the size of the pre-trained model we use or anything else? And right now I would like to start with Noam and then Rishabh and everyone else.
Yeah, I mean, I think the one way that I think about scaling up, the inference time compute paradigm is just in terms of dollar value. So if you think about how much it costs to query ChatGPT for like the 4.0 model, it's, ballpark plus or minus order of magnitude a penny. How much would people be willing to pay for answers to some of the most important problems that they care about? I would say at least $1,000 for like really hard problems, up to probably past $1 million for like some of the most important research problems that we care about. I mean, the prize for proving the Riemann hypothesis is $1 million, so you can spend at least that and still come out break even. So that's 8 orders of magnitude to go from 1 penny to $1 million. So we've already scaled up to some extent with 01. Like 01, you can look at the the API cost. It's like more expensive than it is to query 4.0, but it's still nothing compared to what it could be. So I think there's a lot of room to scale that further.
All right, Rishabh?
So I think there was a mention of tasks. So I guess maybe coming back to O1, like let's say it works really well on things like math puzzles and coding and whatnot. But then there's a lot of these open-ended tasks which are hard to verify, which I guess it is a challenge. And maybe I'll just say a controversial statement here that it seems like verification or learning these reward models is still one of the main bottlenecks of getting systems like O1. Because let's say if we do have that, then we can use methods like O1 or other things to optimize that reward, right? So it does seem like that is one of the main bottlenecks, and that does limit the potential of this inference time compute. That said, maybe it's not that hard to find that signal. So there are currently like a few ways we do things. Either we copy humans or we ask human for preferences. And I guess one question worth asking is, what happens when these things don't work? Like when, let's say, humans are not able to tell is this good or not. Like for the really hard problems Noam was mentioning that we really care a lot about, what do you do then? And I think that's where we want to really use this inference time compute thing on. But I don't think it's a solved problem yet. Like it still seems a bit further.
All right, and everyone else who want to chime in?
Yeah, so I think I think for everything where we have a ground reward, and we sort of touched on this, it's a matter of budget. Right? If you give me enough samples, I will eventually find the right answer for you if I can verify it. I think for the case that are not verifiable, my intuition is that it goes back to what we discussed earlier, the question of meta. Right? What if you optimized yourself to be better at searching in those domains? And this also goes back to the proposal that was made earlier, which is, can we learn to search during pre-training? Because that was the project we tried to do in my lab, which was not trying to search only for specific domains, but instead learn to reason at the pre-training scale. And I believe if you self-improve for chain of thought on the data of the pre-training, where basically every token prediction is a task, then I would expect that this would generalize downstream, just like pre-training itself has generalized to a lot of downstream tasks. And I think at that point, probably the limit will be compute. And in particular, being able to deploy all these compute resources during pre-training. Because then the question is, can you actually scale beyond what you've learned to reason? If I only learned to reason for a chain of thought of 10,000 tokens, can I go to 1 million tokens? And that part, I think I have no idea if that will work.
Great, thank you.
I think there's one limitation on the training data for these models, like for math and reasoning or code generation. It's actually very easy to generate a massive, like it's a matter of, there's a bottleneck for the computation, but it's very easy to generate such data for training. And then you might realize that when you train with this data for the model, it's hard to generate on other tasks, not only for like the ones that are not verified, but it's more of a bias towards solving those problems like better, but the other ones, like there's auto distribution problem too, right? Like people might observe, like if you like see the feedbacks from using those models, many users will say, "Oh, it's so great because like the tasks they use it for are great." But there are other ones, okay, it doesn't even solve the problem it used to solve. So I think there's a balance, like it's probably about the training data problem. I think currently, except for the computation, I think it's a limitation on that too.
I see.
Yeah, very quickly. I think RL plus search can be relatively easy to scale in domains where outcome supervision is available, like exactly for math and code, but it's not the case for tasks like writing, biology, drug discovery, etc. And these are the tasks I think we need to really spend more time and effort thinking about how to do meta generation algorithm on. And I think this is because just these algorithms work very well on tasks where a structured step-by-step reasoning is available and verification is easy. And so there is also the other problem of ambiguity in correctness of the response. And so I guess, and there is also the cost of a human verification. And so basically I expect that there will be lots of divergence between what these models, what these systems and algorithm can do on math versus other domains. The other thing I want to mention, even for math and reasoning, as was mentioned during the tutorial, they are bottlenecked by the verifiers quality. And so I think if you cannot distinguish between false positive and true positive, even scaling the compute wouldn't solve that. And yeah, I want to stop here to leave.
I have actually one more set of tasks where this might fail. So far there was an implicit assumption that verification is easier than generation, and that's generally true, like NP problems and a lot of other problems. But then there are other problems where verification could be harder than generation. So think of tasks where you have to verify for a large set of inputs or a combinatorial set of inputs. For example, determining whether a program is safe for all possible inputs. This is verification is actually harder than generation in this case. And I don't know how would we actually tackle these kind of problems, because they're you can't just apply RL, because learning your verifier or getting a reward function is not that easy.
Yeah, I agree. Very, very quick thing.
Oh, yeah, sure.
So I think, so we're talking all the time about very complex reasoning problems and how these systems can be amazing in solving them, as long as you have a constrained domain, and so the model can solve that. Now, actually, I want to ask this question. How about a very complex system that can have reasoning, step-by-step reasoning, but these are things that humans haven't been successful yet in solving, like very complex societal issues like poverty or like a climate change. Would these models be able to solve? Would they be able to solve something that humans haven't yet? So yeah, I think that's another limitation to these algorithms.
Okay,
Right.
I have another.
Oh, yeah, sure. Betty, go ahead.
Yeah, so we recently are looking at the architecture, like transformer architecture kind of limitation. So I think there's a paper last year or earlier this year about the illusion of SSMs, kind of like talking about the state tracking problem should be easily solved with one-layer RNs. But for the other linear models and including transformer models, it's just the number of layers you need and the sequence length or the states that you need for solving this problem is growing not constantly. So I hypothesize that this might be related to even coding, reasoning, those complex tasks as well, because they might need, when we talk about model scaling and test time scaling or COT, is intrinsically adding more steps to resolving those states. But maybe they're going to be research on the architecture side, trying to get both worlds too.
Great. That was a great discussion. Thanks a lot for all the inputs. And now I want to go over to the efficiency part of inference, because as you know, recently we've got so many awesome advances with VLM and other engines. We couldn't think about generating that fast a couple of years ago. And I'm curious, how do you think, is there a wide space for further optimizations within that architecture we have? Or we kind of just waiting until NVIDIA releases new accelerators with even faster frequencies? So, because I think it's really interesting how this was addressed from different perspectives: page attention, continuous batching, context, this prefix sharing or caching, and so on. And I'd like to start with Betty and on here.
Yeah, so I think my answer to the first question are related to this. So if you don't want to change anything about your model and the way that you do repeated sampling and you nothing was changed, it's a little bit hard to like completely optimize from the system perspective. However, if you are like what I mentioned before, now the test-time scaling gives you another degree of freedom to redesigning the algorithm or the modeling part. If you don't get some answers with one try, like multiple tries, might have a better scaling. We actually see that in the early experiments. So from that, if you are willing to change your model and your architecture kind of co-design, then there's a wide spectrum of co-design with the hardware as well.
All right. And could you say about transformers?
Yeah, I think to go down even to the lowest level, talk about hardware, I think there's a lot of opportunity at the hardware level to reimagine things. I think a lot of the hardware that's been developed was designed in a world where there would be a lot of compute spent during training, and then inference would be relatively cheap. And I suspect that we're going to head towards a world where inference is going to be a large fraction, a much larger fraction than of the total compute that is spent for these models than it was before. So I think in many ways some of the most exciting research to be done is at the hardware level. And I would love to see creative ideas for how to make inference a lot cheaper, and in a world where you don't have to worry so much about the constraints of the pre-training paradigm.
All right. I think we are officially out of time right now, but we could get some other other thoughts if you want, just kind of short.
What was that?
I mean, we're out of time, but if anyone has other thoughts,
okay. So I can always speak. So I think another place we'll see a lot of gains outside of hardware is, are you going to use an LLM or are you going to do something else, right? So it came up in the tutorial, I think, the question of tool use. But what if we had integrated systems that could use code whenever it's useful and use inference passes whenever that's the most efficient solution? So I think these hybrid architectures of code and trained components will be absolutely amazing. And I do also agree that just rethinking the algorithms we use for a world where we do trillion times more inference tokens than we do compute training time tokens is really, really exciting. And I can imagine we'll just completely reinvent the entire pipeline for this.
I guess one thing to add to that is, I guess there was a lot of talk about verifiers, and I think that recently there is this line of work which says that rather than treating them as classifiers or scoring models, why not you just treat it like a language model? So generative verifiers or generative reward models, and now all the things you do to language models, like the inference time compute for generators, now they should be applied for verifiers. So what if we have an Owen-style model, but just for verification? And now we can go to the meta thing Jacob was mentioning, that this could be just a single model, which is a verifier and generator, and it's doing its own thing. We are not there yet, but hopefully at some point we might get there.
Yep.
Probably a concluding note from me. I think over the past 5 years or less, we have spent a lot of time thinking about scaling the training law, the pre-training scaling law, and we haven't focused at all on inference scaling law. And so I think there is something very important now to really invest time and effort on, is the balance between pre-training compute and also inference time compute. And what is very exciting for me is that these algorithms can actually enable smaller, more efficient, more compact, model that are specialized, but they can be complemented with these algorithms to unlock more capabilities. The other thing I want to say is that probably we have to think more about the training. I mentioned that earlier, but I would love if we think about that as a community. And also the open source community is lacking lots of these tools. So it would be great if also the open source community focus on that over the next few months, years.
Okay, I'd like to thank our panelists again. Thanks a lot for attending this panel, and we wrap it up at this point. Thanks everyone for attending.